let's see, Vanessa's here. Alondra, did I get Alondra? I got Alondra, okay. Speed, and two more? Can I have two more? One more? Just one more? I know. I'm stalling for a couple seconds because as soon as I hit the button, somebody will show up. Watch. 3, 2, 1, submit. Strange, that usually works. All right, well, good afternoon, everybody. Welcome back to geometry with some awesome problems to solve and some awesome solutions to ponder. Today, I'm going to go over the answers for the prior problem set 1. That was only the first, and now we've got problem set 2 from the same section. Okay, it continues on with more problems. There's more juicy nuggets of interesting knowledge hidden in there. I don't know if you quite realized this, but in solving these problems, you do gain something unique of it. So now, having answered these questions about, say, this structure of equilateral triangles, you'll have a new appreciation for next time you see this kind of a picture, right? So next time you play Legend of Zelda, you can be like, well, what if the Triforce was actually a 9-force, right? That'd be cool. Okay, somebody did actually just chime in. Leslie, there you are. Okay. So anyways, please take out your work from problem set 1 and compare your answers to mine. Reminder that, yes, I do check your homework. I go through it and I look at it, but I don't individually check your correctness on every problem and check that through. I just give you points if it's there. So it is up to you to compare your work to the correct answer so you can actually see how you're doing. If you did things correctly. If you didn't do things correctly and you don't immediately see how the answer is the right answer, then please ask me more questions. I'm happy to explain it further. So number 1, how many equilateral triangles in this 3 by 3 by 3? There are a total of 13 of all sizes. Big, medium, and small. Don't forget the ones that are upside down. Next up, we have the Tetromino question. How many possible unique Tetrominos are there? Well, if you are at all experienced with Tetris, you'll be able to name them all, except Tetris includes some reflections, right? They said they don't count if you flip them over to get something new. So the L and the J from Tetris are the same piece, and the S and the Z from Tetris are the same piece. So that really only gives us 5 totally unique options here. And then the third level 1 question, how to fill in 6 of 9 squares so that you get no horizontal, vertical, or diagonal 3 in a rows. Like this, you actually have to put the empty ones in a diagonal 3 in a row, and you kind of shade in these little L corner squares here. And this way, you never get 3 up, down, left, right, or even the diagonal. This diagonal gets blocked by that diagonal, which is completely different from this one. I can't just go diagonal with my 4 blank squares because of the fact that it's an even number of squares. I don't have a middle square that is on both diagonals. So if you make this blank and you color in these 2 white ones instead in the center, you would then have the 4 in the diagonal row, and that would screw it up. So you have to spin this around a little bit, but we still have this, like, suggested these corner bracket kind of pieces. So it's a similar pattern, but not quite the same. All right, any questions on those first 3 problems? No, let's go on to the level 2 problems. We went on to the pentominos. Tetrominos were great. Pentominos could be even better. So here we have 5 squares, and we can now make 12 unique combinations. If anybody's played the game Blockus or Blocus, it's a wonderful board game. You got these colorful little pieces, just like this, but all of the sizes. You got the omino, domino, triomino, tetra, penta, right? All 5 sizes. And these are the biggest ones, and thus the hardest to get on the board properly. So there they are. And yes, you can totally stick 5 of them together to make a perfect 5 by 5 square. Here is one of many, many possibilities. Okay, there's lots of different ways to do it. This is only one option, color-coded for your convenience. And 3 of them can combine to form a 3 by 5 rectangle. Actually, this is rather simple. This is one possibility here. There are several others, not quite as many as the big square, though. And finally, if you went all the way to level 3, you dealt with the hexominos. This is 6 squares all together, and what's unique and wonderful about 6 squares is that they can fold up to form a 3-dimensional cube. Right? You could make your own like custom dice by printing this thing and cutting it out and then folding it and taping it up. And then you could say, okay, what number ends up opposite the 1? So to do this without an actual paper prop relies on your visual spatial reasoning skills. You need to manipulate this item box in your brain in 3 dimensions and wrap it around. So I've tried to kind of draw the results of C here. So if you start with 1 as your front face here, and then we fold in 3, kind of wrap it around to the side there, ends up along the side here, and then you can fold 2 down, and really I should have written the 2 as it'd be a sideways 2 as it is printed there, because this edge would fold down and match up with this edge. And the 4 would fold up to form the bottom, so the 4 is on the bottom of the box, and then the 5 attached to it would fold up from the bottom and then be on the back side. And then off of there, the 6 would then fold, and it would actually get wrapped around to the left side here. Right? Any questions on those problems? No? All right, then prepare for problem set 2, more of the same but different. The same strategies can be employed, but now we've got some new scenarios to consider. So first up, we have the toothpicks. Good old toothpick problems. Always great fun with toothpicks. Here we have a 2 by 3 square arrangement. From this, we want to remove 6 toothpicks and leave 2 squares. Okay. And then in part B, remove only 5 toothpicks and leave 3 squares. Now, when it says there should be no leftover toothpicks, that means notice how every toothpick already on there is part of a square. You can't have like a square and then one stick pointing off to the side like that. That stick does nothing. That's not allowed. Right? Every toothpick has to be part of a full square. Okay? But I didn't say anything about the size of that square, now did I? Might make use of that. Okay. Next up, you have number 19. Can you trace the following figure without lifting your pencil and without retracing any lines? All right. This is a wonderful little lunchroom kind of puzzle to challenge your friends, right? Get some paper and say, hey, can you draw this shape without lifting the pen? Or retracing, right? So if you can find out a way to do so, don't just upload your picture of the shape, because then I have no idea if that worked or not. Instead, what I'd like you to do is detail your diagram a little bit. Give us a nice big dot where you started. And along every line, give us a little pointing arrow, what direction you're going, and then number each segment as you add to it. So especially if I have like a crossover here, right? I go up 1 here, 2, 3, 4, and then 5 there. So I know that, oh, I didn't go this way, or I didn't go here, then turn there, and then come back, right? I know which direction you went in what order. All right? That's how you can actually convey your solution without having to like write a giant paragraph trying to describe turn left. If it can't be done, I want you to be sure that it cannot be done. Not just, oh, I never found the solution, I give up, the answer is no, it's not possible. But you have to have a reason for why it's not possible. Okay? Either you have actually exhausted every single possibility, which on one of these drawing things seems unlikely, okay? Or you've encountered like some obstacle that just mathematically gets in the way. You can say something like, well, the fact that it has 4 corners actually inhibits because it needs to be a multiple of 3 or something like that, right? you've got some rule to follow, and this one breaks the rule, therefore it can't be done. Okay? Some specific instance you can point to, be like, this guy right here is the cause of all my issues. You can't get past that. It's not possible. Something like that. All right, and then finally, for level 1, we have a child has 10 blocks with heights of 1 centimeter, 2 centimeter, 3, 4, 5, 6, you get the idea, right? All 10 sizes, centimeters of blocks. The child wants to use only these 10 blocks, and I should specify here, all the blocks, to build 2 separate towers that are exactly the same height. Can this be done? If so, how? If not, why not? Okay? So again, you're testing combinations here. This one might be a little more reasonable to try to exhaust. Just try every combination, see what happens. But that would be literally exhausting. Okay, it's going to take a while. See if you can find maybe a pattern there. Maybe draw to help you out. But just to give you sort of an idea of what we're looking for, make sure you fully understand this problem. Right? Here is a 1 centimeter block plus the 2 centimeter blocks makes a 3 centimeter tower. And just the 3 centimeter block makes itself a 3 centimeter tower. So there's 2 towers of the same size, but using different blocks. But we want to use all 10 blocks. That's the challenge, right? That this is easy. Just use 3 blocks. Hey, you're done. No. All of 10 blocks, but only these 10 blocks. You can't borrow another 8 block from the neighbor. All right? There. My hope is that this intro will iron out the kinks, and so you can get through step 1. You now fully understand each of these problems. If not, please ask me more questions. So you will be all set to start devising your own plans and carry them through. If you finish with these, go on to level 2. Okay, the level 2 problems are just as good, if not better, than the last ones. Okay, there's some awesome stuff going on in these questions. Really neat mathematical possibilities to consider, and only so much time to deal with them all. All right, but that's enough from me. I leave you the rest of the period to work, which is like a lot of minutes, okay? Almost more than 30 of them, all right? Have at it. Please stop and ask me any questions. If you get stuck, I'm happy to help you out or give you a hint or a nudge, whatever you desire. Okay, that's it. That's your assignment, okay? These are due Friday. Go.